Hey everyone, welcome back. This video is a short example of how to use the Work-Kinetic Energy Theorem. And there's a reason why this is my favorite equation to use for the energy unit. So here's an example. Let's say you have a car, and like always, my drawings are awesome. And this car is supposed to be driving on a nice level road. And let's say that it has a mass of 1,600 kilograms and it's traveling with an initial speed to the right of 25 meters per second. A lot of problems are really annoying and put things in kilometers per hour, but we're going to keep it simple. So let's say that this car is about to hit a rough patch or rough surface. Right now there's no friction where it's traveling, but it's about to hit a rough patch where the coefficient of kinetic friction, because it's moving, is equal to 0.4. And let's also say that this rough patch is 50 meters wide. Okay, so what we want to find out is how fast is the car traveling after it goes through the rough patch. Okay, so we need to go back to the work-energy theorem, which says that the total or net amount of work done on an object is equal to that object's change in kinetic energy. And this is what I like so much about this equation, is that if you think about all the forces that act on an object and carefully analyze them, then you can calculate the net amount of work. It's pretty easy. So in this case, let's draw the forces acting on the car. Okay, so when it's in the rough patch, there's the rough patch, and there's the car, okay, and the rest of the road is wherever. So in this location, well, what forces are acting on it? Okay, well, you got gravity. You're going to have a normal force, but now in the rough patch, it's going to also experience friction. And this friction is going to oppose its motion. So this is going to be kinetic friction pointing to the left. Okay, so keep in mind this green arrow is just the velocity. It's not a force. Alright, so now to really use the work-energy theorem, we have to take each of these forces and figure out how much work is done because of these forces. So we have work due to the normal force. We have work done by gravity, and we have work done by friction. And that is going to give us kinetic energy final minus kinetic energy initial. So even though I'm listing all three of these forces, they don't all actually do work. If you think about it, the car is moving to the right, but the normal force is pointing up. So we have a case where a force is pointing up and a displacement, because that's the way the car is moving, is at a right angle. So when we get into it and we calculate the work done by the normal force, it will be FD times the cosine of the angle, and that's going to be equal to the cosine of 90 degrees, which is 0. For a reminder of this, you can look back at the work energy video. So that's going to be equal to 0. So what this means is that as the car travels to the right, the normal force is not doing any work. For the same reason, neither is gravity. Friction is another story. For friction, we're going to have to calculate the force of friction and multiply it by the distance, and then multiply that by the cosine of the angle between them. And then that's going to give us kinetic energy final minus kinetic energy initial. Alright, so let's remember what we know about the force of friction. Depending on how you learned it, in my class sometimes we talk about friction is equal to muffin, mu times the force normal, muffin. So we can put into our equation that the kinetic force of friction is mu k times the normal force times distance times the cosine of the angle. And that's going to be equal to 1/2 mv final squared minus 1/2 mv initial squared. Remember that kinetic energy is always 1/2 mv squared. Okay, now also remember that the car is just moving to the right. It's not accelerating up or down, so that means that the normal force and gravity are going to be equal to each other. So they'll be equal in magnitude. So mu times mg times the distance. Okay? Then we have to think about the angle between the force of friction and its displacement. So most of the time friction is going to do negative work, and the reason is that as the car is chugging along to the right, friction is going to be to the left, and that angle is 180 degrees if you start at one and go to the other, and the cosine of 180 degrees is -1. Okay, so there's going to be a -1 right there, and we'll have 1/2 mv final squared minus 1/2 mv initial squared. Alright, now at this point, another neat thing we can do is because each term has an m in it, we can cancel that out. And so what we have is mu k times gravity times distance with a -1 is equal to 1/2 v final squared minus 1/2 v initial squared. And if this looks familiar, this looks like what we might have called the forgotten equation before. That's because it is. Take a look at the derivation video to remind yourself where this comes from. In this case, mu times gravity would be the car's acceleration. Okay, so let's solve this for v final because that's what we want, and then we'll plug and chug. So we have 1/2 v final squared is equal to 1/2 v initial squared, minus mu times gravity times displacement. Multiply everything by 2 and take the square root, and we have v final is equal to v initial squared minus 2 mu g times d, and then the square root of everything. Now of course you can plug in numbers way up at the top here, and that's fine, but I like to show how it can be a little bit easier if you put in the numbers at the end. Okay, so let's plop in some numbers. I think we said it started with a speed of 25 meters per second. We square that. I think we said that friction was 0.40. Gravity is 9.8 meters per second squared, and we do not put in a negative sign for that, like we've talked about in the past. And the distance that it travels is 50 meters. Okay, so I'm going to grab my calculator here. So we're going to have the square root of 625 meters squared per second squared minus 392 meters squared per second squared. And if you don't believe me on the units, check it out. You got meters times meters and seconds squared. So that's going to be the square root of 233 and that comes out to be something like 15.3 meters per second. And that's going to be our final answer. Now one thing to check when we get to this final answer is to see if it makes sense. It doesn't make sense that a car going through a rough patch would have a lower final speed than it started with. And I think the answer to that is yeah. So that pretty much wraps it up. I'll try to do a couple more examples a bit later.